Welcome to this explainer. Okay, today we're putting on our detective hats. We're going to meticulously unpack a really critical machine learning algorithm, expose a fatal mathematical flaw that hides deep inside its logic, and then we'll explore the brilliant patch that brings it back to life. It's kind of like a high-stakes peck detective story because the real-world implications here are absolutely huge. 4.2 million. Now, according to the World Health Organization's 2019 data, that is the estimated number of premature deaths linked globally to chronic air pollution. And staggering enough, 89% of those cases occur in low to middle-income countries. So we aren't just playing around with abstract math today. We are looking directly at the algorithms that environmental and public health agencies rely on to track air quality, warn the public, and ultimately save lives. If the algorithm fails, well, the safety net fails. So here's our roadmap for today. First, we'll look at the air quality crisis. Then we'll meticulously break down GNB, dive into the zero frequency bug, check out the Parson-Rosenblatt patch, and finally, we'll wrap up with some real-world results. All right, part 1, the air quality crisis. Let's head over to the Philippines for our real-world case study. Researchers needed to track the air quality at the Pamantasan ng Lungsod ng Manila, or PLM for short, and its surrounding areas. You see, studies show a direct connection between poor air quality and a real decrease in students' academic performance and cognitive outcomes. So to safeguard student health, these researchers needed a robust, computationally efficient way to classify huge amounts of continuous environmental data. We're talking things like ozone, nitrogen dioxide, and particulate matter, all distilled into a clear air quality index. To pull this off, they turned to a classic machine learning model. Moving right along to part 2, a meticulous breakdown of Gaussian Naive Bayes. Let's meticulously unpack the star of our show today, Gaussian Naive Bayes, or GNB. Now, you likely already know this is a generative probabilistic classifier, meaning it calculates the probability that a new data point belongs to a certain class. But let's briefly refresh on its mechanical assumptions just to be thorough. First off, it's naive because it assumes every single feature, like, say, the level of carbon monoxide versus the level of ozone, is completely independent of the others. And second, it's Gaussian because it forces the data into a standard bell curve, a normal distribution. While these assumptions definitely oversimplify the messy real world, they actually make the algorithm incredibly fast, highly computationally efficient, and generally very accurate for continuous data. Structurally, the algorithm follows a very clear step-by-step process. Step 1, data is collected. Step 2, the data is normalized. It basically standardizes the features to a common scale, so a massive variance in one chemical doesn't completely drown out another. Step 3 is the core engine. Using Bayes' theorem, it calculates the prior probability, basically how often a class occurs generally, and the likelihood of the current features given that class, based on that Gaussian bell curve we just talked about. Finally, step 4, it multiplies these together to get the posterior probability and assigns the data point to the class with the highest score. And you can see exactly how this math plays out visually right here on this scatter plot. The algorithm looks at continuous data points, represented by these dots, and calculates the probability densities to draw these smooth, color-coded decision boundaries. It neatly partitions the unknown world into defined zones. If a new data point lands in the red zone, boom, it's classified as red. It's elegant, it's mathematically beautiful, and honestly, it works wonderfully, most of the time. Which brings us to section 3. The zero-frequency bug. But you know, the real world loves to throw curveballs. Enter the villain of our story. What happens to our perfectly structured algorithm when it encounters a feature value during testing that was completely absent from its training data? What if it sees an extreme outlier, or a specific weird combination of pollutants it has literally never seen before? Well, the crucial point is this. The probability breaks entirely, because the naive Bayes algorithm relies on calculating the joint likelihood by multiplying the probabilities of individual independent features together. And we all remember basic math, right? Anything multiplied by 0 is 0. If there's no prior knowledge of a specific instance, the algorithm assigns it a probability of absolute 0. That single 0 dominoes through the entire equation, wiping out the influence of every other perfectly valid feature. The algorithm basically throws its hands up, perceives the outcome as completely impossible, and gives you a completely inaccurate classification. Let's look exactly at where this infection happens. On this flowchart of the traditional GNB process, focus your attention on the bottom right side. During the testing phase, the data flows into that red box labeled likelihood. Because it's trying to fit new, unseen data into a rigid Gaussian bell curve built only on past training data, a random outlier causes that likelihood box to spit out a 0. It completely bypasses the logic of Bayes' theorem below it. The whole system fails. So how do we fix this? Enter Section 4, the Parson-Rosenblatt patch. Those researchers at PLM obviously couldn't afford for this system to fail when classifying crucial air quality data, so they implemented a really elegant mathematical rescue, the Parson-Rosenblatt window method. Let's meticulously unpack this. It is a non-parametric density estimation method. Unlike traditional GNB, which rigidly forces data into a predefined bell curve parameter, this method is actually flexible. It looks at the actual data points and places a small window, or a Gaussian kernel, over each one. It calculates probability by looking at the surrounding neighborhood of data. It basically assigns a weight to nearby instances that decreases as distance increases. So even if a new test point lands in an empty, totally unexplored area of the map, the distance surrounding data points still exert a tiny bit of gravitational pull, contributing a fractional weight. And the result? The probability never, ever equates to absolute zero. Look at our enhanced flowchart here. Right in the middle, the rigid calculation of prior probability is now feeding into a purple box, the Parson window for density estimation. This seamlessly replaces that flawed likelihood step. It's a kernel tweak that acts like a shock absorber for the algorithm, ensuring that rare events or noisy datasets don't completely crash the multiplication process. Okay, let's get to Section 5, real-world results. So the math checks out in theory, right? But how did this meticulous enhancement actually perform when deployed on real-world environmental data? Let's check out the numbers. The researchers tested this on two major datasets, the Open Weather Air Quality Index and the USAAQI. On the Open Weather dataset, you can see a solid 2.39% improvement in accuracy. But look at the bottom row. The USAAQI dataset is highly complex and has a much higher class imbalance, making it a total minefield for the zero-frequency bug. The traditional model struggled there at 59.33%, but our enhanced model jumped a massive 5.26% to reach almost 65% accuracy. By smoothing out the probability density, the patch proved its worth exactly where the algorithm was most vulnerable. And it wasn't just raw accuracy either. Across a standard 80-20 data split, the enhanced algorithm consistently swept the board. It delivered better precision, meaning false alarms were reduced. It delivered higher recall, showing much better sensitivity to actually capturing bad air quality days. It produced a stronger F1 score, which is a great balance of both. And absolutely most importantly, the zero-frequency bug was completely mitigated. The system was finally stable enough to be a highly reliable tool for public health monitoring. We rely on machine learning for literally everything these days, from predicting traffic to diagnosing diseases and monitoring the very air we breathe. Today, we saw how a tiny, inherent blind spot, just the assumption that a zero is an impossibility, could derail an entire system, and how a meticulous mathematical patch saved it. It really makes you wonder, if a simple kernel tweak can save this algorithm from failure, what other mathematical blind spots are hiding in our critical prediction systems? It's a great reminder that behind all the magic of AI is just math, and math always requires a meticulous eye. Thank you so much for joining me today on this explainer, and keep questioning those algorithms.